Hey again, it's Mr. Allred. Last time we left off, we had Riemann sums. We were trying to find the area under a curve, and we were making an infinite number of rectangles. So we had the curve, which might be f of x. We had an interval under that curve, starting at a, ending at b, and we had an infinite number of very thin rectangles. And we're going to introduce a new notation that is a definition. And so that means it has its meanings, and once you understand its meanings, you can do wonderful things with it. But it's a leap of faith or an acceptance as far as getting there. And just to kind of backtrack a little bit, I want to show you when you were introduced to a logarithm. Basically, the relationship as far as a function definition between an exponential, in this case b to the c equals a, being able to be converted or related to a logarithm, log b of a equals c, is a definition. We saw that maybe we want to be able to solve for that exponent c up there, so we had to find a way to get it by itself. So that's a definition, but once we had that definition, we could do many things. Okay? So that's kind of where we are now. We're going to take the idea that we left off with last time, okay, which is this limit definition. Now I copied this from somewhere, so it looks a little bit different than when we had it in the last video. But basically, we've got infinitely thin rectangles. We got height, we got width. We're adding them all up. Okay. And that would, if we could do that properly and actually do an infinite number of rectangles super thin, we would get the actual area under a curve. Well, turns out it's not really hard to do if you kind of bypass that procedure. And it's probably a several lecture event to show how you can get there. But we're going to take the power of the definition here of where it leads, and we're going to introduce some new notation. So what we have on the left-hand side is something that we're going to say is equivalent. We still see the function height here, f of x, and we see dx, which is a change in x. That's a width. So we've still got a width times a height. So those are rectangles. What we have here is the integrand, or the integration symbol. It looks like a kind of a curly S. You see it there at the bottom, and you see the endpoints A to B. So basically what this is defining is a space under the curve f of x from starting at x equals A and ending at x equals B, and gives you the area. So it's a much cleaner notation than the one on the right with the limit definition using sigma. But it's very new, so it's very foreign. So it's not that easy to work with your first time. But actually it's not very hard to actually handle, and we'll see that in a moment. But we call this the definite integral if we have two values over here, a and b, a start and a stop point. And there's names down here. The function is called the integrand. The dx is basically, I said that was a width, and that's what it is. Dx means change in x, the difference in x. And if you happen to have multiple variables in a function, the dx tells you that x is the one you're really measuring everything in. So let's go down here and let's just talk about what this information means. So we're very used to derivatives, and now we just introduced this thing, the area under the curve symbol, and we're calling it integrals. Integral is the proper name. A less educated term used is antiderivative, and it really gets you thinking about a link between derivatives and integrals. So if you want to call an integral an antiderivative, some people will kind of shrug at you and try to correct you, and that's fine, because you really shouldn't call it that. It has some extra connotations. But as far as thinking and trying to get used to what's going on, that's probably the best concept you could think. Derivatives, antiderivatives. If you think of taking a derivative, an integral is the opposite of that. It's kind of undoing a derivative. Okay. So just to kind of get some notations for where we're going, derivatives. We're used to that if we have a function, we call it f or possibly y, we'd say the derivative is f prime or y prime. Okay, and we could calculate that using some of our derivative rules. A notation that's kind of common for where we're going is sometimes we'll call the original function capital F and the derivative lowercase f. That still ensures a link. But if we're going to undo something, we don't want to call it a derivative to start with, so that's why the antiderivative phrase is kind of frowned upon, because you're turning it into a derivative when it possibly never was. Okay? So when we talk about integration, we're just kind of flipping those around. If for some reason you saw f prime and you wanted to do the integral, you could call it f. If you saw lowercase f and you wanted to do the integral, you could call the resulting function capital F. Okay? It's a little bit confusing at first, but hopefully you get used to it without too much trouble. And just practice is what's going to take care of things. There's two things to have here, and then we might see an example. But over here on the right-hand side is what we're integrating. There's our function. It's in terms of x. You don't see any endpoints here. So lowercase f is the function we're starting with. We're taking the antiderivative, the integral, so we'll call that function big F. So basically if we took the derivative of capital F, it would give us lowercase f. Now the extra perk of doing this is that since we're starting with little f, we don't necessarily know exactly where it came from. And if you think about some of the functions we had, if we had a number at the end of them, if we had like plus 5 and we took the derivative, we'd never see that in the derivative. So we never knew that 5 was there if we just saw the derivative. It could have been 2, it could have been -7, it could have been anything. So if we're reversing the process, we need a placeholder that would pick up some type of constant. Okay. Now this is if there's no a or b here, no numbers. So what we have down here is we have the definite integral where there are numbers. So the original function up here, the indefinite integral, gives you a function. Okay, as a result, the definite integral gives you that function, but then you're going to plug in these values. So when you plug in b, basically that gives you the area from 0 back to b. And when you plug in a, that gives you the area from a back to 0. If you take the difference, that would give you the area between A and B. Okay? Alright, so we will see some examples of how this is used in the next video. But you got to get used to this notation, so kind of keep this file open and refer to it.